Hello students. So in this video, we will discuss about the mesomeric effect applications. So what are the applications? So how to uh, identify the stability of that molecules in a mesomeric effect conditions. Okay. Now in this first condition, this one is one benzene group only. If this group has, suppose consider this one is the electron releasing group. Okay, electron releasing group only. Electron releasing group means this one has a lone pair of electrons. The lone pair of electron present on the given compound, if it is donate the lone pair of electrons to the adjacent system. If it is donate the lone pair of electrons to the system, these pi bonded electrons moving towards to adjacent carbon atom. Why? Because here density increases more. Already it has pi bonds. Then next it convert into another form. This symbol is the resonance symbol only. Now this one converts into. Here this carbon get the charge negative. Here this one get the double bond and one positive charge on the G. Next, the remaining all pi bonds are alternatively present. In these given conditions, if here density increases more on the this position, okay, more immediately it donate electrons to adjacent carbon. These pi bonded electrons comes to this carbon atom. Then this is the symbol of resonance only. Then after that, this is the structure. In this structure, it has one bond. This one has a negative charge. Here another pi bond. Here a double bond. G. Here positive charge. Then immediately this one again involving in the delocalization. Why this one involving in the delocalization? Here this carbon has more number of electrons. The density is very high. Immediately donate electrons. These pi bond electrons comes to here. Then this group converts into like this. Here this carbon get the charge negative. Here a double bond. G plus. Here one double bond. Here one new bond develops. Then finally here this one donate electrons to adjacent carbon. Here pi bonded electrons moving towards to this G plus. Why? Because here plus means it indicates positive charge, required electrons. Finally, it gives the final structure is single bond G. It has a lone pair of electron. Here alternative pi bonds. So these are the resonating structures of which one? If any electron releasing group present on the benzene. Electron releasing group present on the benzene. Now in this case, benzene acts as a pi system. It has three alternative pi bonds. Then after that, so what we will discuss in this case. So this is the main group with respect to that. This position here, positive charge developed here, negative charge developed, negative charge developed here. This is the ortho position. Here also one negative charge developed. This position is para position. Again here one more. This is ortho position. Totally two ortho and one para position only influenced by the electron releasing group on the benzene. So at which position here electron density increases? Electron density increases at ortho and ortho and para positions. Ortho and para positions. Just identifying this ortho and para positions only, so that bond, that means negatively charge is increased on the ortho and para positions. If electron density increases more on the ortho and para positions, but but not on the meta position. So meta position is not influenced by any group present on the benzene, either whether it is a releasing group or electron withdrawing group. Then finally, what is the conclusion in this? Now, electron releasing groups always increases the density at ortho position and para position. So that's why these groups act as the ortho para directing groups. Ortho para directing groups. So by using this condition, what is the meaning now? So actual meaning, if it is actually as ortho para directing group, means here whatever the group is attached to benzene, this group here acts as the ortho para directing group. So ortho para directing group indicates here the main condition. Now look here, all of you, in this. If any group which is attached to the ortho and position and ortho and para position, ortho and para position, in that case, mesomeric effect influence. Mesomeric effect influence. Whether that mesomeric effect is either plus M or minus M, whatever the group. Okay. Or the para position, if any group is attached to that, mesomeric effect only influence. Okay. Then if a meta position, any group is present, if the group which is presented meta, so only inductive group, only inductive effect influence, only inductive group influence. So whether that group is plus I or minus I. So whatever the group, if any group attached to the meta, plus I or minus I only influence. If the group which is attached to ortho and para portion, either plus M or minus I only influence. So these conditions very important. Okay. So based on that, here if any condition based on the given, what are the applications we will discuss now? Applications. Applications. So in the first one, it explains stability of allyl and benzyl carbocations. Allyl and benzyl carbocations. Next, second one, it explains stability of allyl and benzyl carbene ions also. Same like carbene ions, carbocations like carbene ions. Next, third case, it explains stability of allyl and benzyl free radicals. Free radicals. Okay. Next, fourth condition, it explains stability of molecules and ions. This one also very, very important. Fourth condition also we will discuss stability of the molecules and ions. Next, fifth one, it explains acidity of, writing directly, it explains acidity of phenols and benzoic acid. Okay, it explains the acidity of which one? Phenols and benzoic acid. That means this phenol is nothing but aromatic alcohol. Now benzoic acid means aromatic carboxylic acids. Next, sixth application. It explains basicity of aniline. Aniline means aromatic amine and and amides. So these are the few important conditions. And another one also we will discuss in this seventh case. It explains bond lengths, bond lengths and dipole moment of the molecules. Okay, so these are the applications. The next, so based on that conditions we will discuss now. The first application is stability of allyl and benzyl carbocations. So now it is very, very important only. We'll discuss now. First step. First one, stability of allyl and benzyl carbocations. Stability of allyl and benzyl carbocations. The next, so first I will show you the allyl group and benzyl group. Okay, right. So which one is the allyl group here? Allyl group is CH2 double bond CH2 plus. This one only allyl group, allyl carbocation. Next, another one is benzyl. On CH2 group. This one is the benzyl group. Benzyl carbocation, allyl carbocation. So we will discuss now about these conditions only, the stability of allyl and benzyl carbocations. Now it is very, very important. The first condition, the first example, A, CH2 double bond CH2 plus. This is the one compound. Okay. Next, second compound CH2 double bond CH bond CH double bond CH2. Here positive charge. This is the second condition. Next, CH2 double bond CH double bond CH2 CH double bond CH2. Here one positive charge. In these three given compounds, so which allyl carbocation is more stable? So here three allylic groups attached to this condition. So here it is one allyl group, two, here three. In the second case here one, here two. But in the first case, one only. So if the number of allyl groups increases, that means CH2 double bond CH groups increases, resonance increases more. Okay. So this one also donate the electrons, one condition. This one also donate electrons. This one, three possibilities. Then if you observe in the second case, one, two, here only one only the possibility. Now, which one is more stable carbocation in this? By using these cases, C is always more stable than B, B is more stable than the A. This one is the stability of allyl carbocation. So more the resonating structures, more will be the stability. Here how many possible? 6 resonating structures possible. In the second case, 4 resonating structures possible. In this case, 2 resonating structures only possible. So these are the resonating structures of allyl carbocations, and these are the most stable compounds only. The next, how it is involving in the resonance, I will show you now. In the first case only, CH2 double bond CH2 plus. This is the carbocation. In this carbocation, this one donate the pi bonded electrons to adjacent carbocation. Now it is a symbol of resonance. CH2 single bond CH double bond CH2. This carbon here get the positive charge. Then again, if you observe in these two cases, now these electrons also moving towards to this adjacent carbocation. Again, the first compound only forms. This is the first, this is the second. How many resonating structures here possible? Two resonating structures. So these are the two resonating structures for one double bond with carbocation. Here two double bond means four possible. First two, second four, next six possible. So this one is the stability order of the given molecules. Next, another example, same as like we will discuss. First one, same like another compound also. CH2 double bond CH2 plus allyl carbocation. Next, compound B. So in this compound B, CH2 double bond CH plus CH3. So this is the another compound. Next, third one, CH2 double bond C bond CH3 bond CH3 here plus. So these are the resonating structures possible in all cases. Why? Because one double bond is present here. Here also one double bond condition. Here also one double bond condition. So here it is donate the electrons towards to this carbocation. So plus R groups are present, or another one is plus M also, plus M plus M. So here plus R or plus M groups are present. So equally the plus M effect is influencing on the carbocation. But in the first case, two hydrogen atoms present, but in this case, one is the CH3 group, it is a releasing group only attached to this carbocation. In the second case, if you identify here also, here, two releasing groups. How many releasing groups? Two releasing groups. So two releasing groups and mesomeric effect both stabilizes the carbocation in the third case. Now, which one is more stable? C is more stable than the B. B is more stable than A. This is the stability order of allyl carbocations. So this is the another kind of example. Next, one more we will discuss another. This is the 5-member ring. Here one double bond. Here one CH2 group plus. Next, this one is compound A. Next, compound B. This one also 5-membered. Here one double bond. Here positive charge. Next, third compound. Here positive charge. Here one double bond. Next, compound D. CH2 plus. Here one double bond. Now, in these four given compounds, how to identify the stability of the carbocation? Stability of carbocation. First, identify the allylic group. Here, alternatively, when CH2, it is allylic group only. Allylic group is present. So, this kind of group is called the carbon one only attached to this carbon carbocation. It is primary allyl carbocation. Now, coming to this one. This carbocation is a tertiary with carbocation and allyl position one double bond here present. So it is tertiary allyl carbocation. Tertiary allyl carbocation. Now coming to this space here, this carbon attached to two carbon and allylic group is also present. Here also allylic group. Here also allylic group. Now it is secondary allyl group. So now coming to the fourth case, in this given condition, there is no allylic group. One pi bond is present and one positive charge. It is just a primary carbocation. It is not a allylic group. So here resonance is not possible, or mesomeric effect is not possible. Plus M group is not possible, or plus R, either this one or that one. Not possible in these cases. But here plus M is present, plus M, plus M. So just now only we discussed in the first case. If tertiary means in the second case, it is allylic group. These are the releasing groups only, like this. These are the releasing groups. Now here also one releasing group and this one donate the electrons, like this. Here there is no releasing groups. So here in these four cases, in these three cases A, B, C, which one is more stable always? The tertiary allyl group is always more stable. So B is more stable than the C. C is more stable than the A. and D is the least stable compound. This is the order of a benzyl carbocations. So in this benzyl carbocations, so it is a very important condition only. Okay. So I think you understand. Did you understand these conditions? Okay, I hope you understood. So by using this, we can easily identify the like this conditions only. The next another one is a benzyl carbocation. It is all are the allyl groups only. These all are the allyl groups. Next one we will discuss benzyl. Benzyl carbocation. So now one resonating structure only we will discuss again in this also. It is also very important. CH2 plus, it is called benzyl carbocation. So in this benzyl carbocation, next here positive charge on this carbon, it required electrons. Now this group alone, it acts as electron withdrawing group. Now this one donate the electrons to adjacent carbon. Then this group converts into here a double bond CH2. Here after donation of the electron, this carbon gets charged positive and alternative double bonds. Okay. Then finally here positive charge, here pi bonded electrons alternatively present. Again, this one donate the electrons to this. Now this group alone it converts into here double bond CH2, here double bond, here also double bond, here positive charge. Then next another condition here. This one donate the electrons to adjacent carbocation. Here positive charge, here double bond CH2. So finally it donate electrons to this. Now here CH2 plus here double bond, here double bond, here also double bond. So these are the mesomeric structures are the resonating structures of the compound. In these mesomeric or resonating structures, so what did you understand in this? This position is that position ortho. This position para ortho. So the CH2 plus group present on the benzene, it decreases the electron density. It decreases electron density at ortho and para positions. Okay, this point is also important. It acts as a meta-directing group. It acts as meta-directing. Why this one acts as a meta-directing means it decreases the electron density at ortho and para positions. So that's why this group acts as a meta-directing group. So these are the conditions. So based on these conditions, now we will discuss about the stability of the benzyl carbocations. Stability of benzyl carbocation. The stability, how it is majorly depends. First one, First one. CH2 plus A it is. Next B CH plus, this is the another group, C plus, this one. Okay, 3 phenyl rings. Here 2 phenyl rings. Here 1 phenyl ring. So resonance conditions more in the third case only. Why? Because more the number of phenyl rings means more will be the resonating structures are the mesomeric structures. Now C is more stable than B. B is more stable than the A. This is the stability of the which one? Benzyl carbocation. It is phenyl carbocation, diphenyl carbomethyl cation, or triphenyl methyl carbocation. So for this kind of compounds, always the third group is always more stable. So more the resonating structures, more will be the stability. So this is the stability order for the given compounds. So the next another compounds also we will discuss in the next video. Thank you.